Alright, so today I'm going to be explaining this paper with the title Diffusion-GAN, Training GANs with Diffusion. This ICLR paper in 2023 from Microsoft and University of Texas. Generative adversarial networks like GANs are challenging to train stably, and promising remedy of injecting instance noise into the discriminator input has not been very effective in practice. In this paper, we propose diffusion-GAN, a novel GAN framework that leverages a forward diffusion chain to generate Gaussian mixture distributed instance noise. Diffusion-GAN consists of three components, including an adaptive diffusion process, a diffusion time-step dependent discriminator, and a generator. Both the observed and generated data are diffused by the same adaptive diffusion process. At each diffusion time step, there is a different noise to data ratio, and a time step dependent discriminator learns to distinguish the diffused real data from diffused generated data. The generator learns from discriminator's feedback by backpropagating through forward diffusion chain, whose length is adaptively adjusted to balance the noise and the data levels. So this part is very important. The generator learns discriminates feedback by backpropagating through forward diffusion chain. Because we know that GAN is unstable in training. And this is a flow chart of diffusion GAN. So the top row images represent the forward diffusion process of real image, while the bottom row images represent the forward diffusion of a generated fake image. The discriminator learns to distinguish a diffused real image from a diffused fake image at all diffusion steps. So you know that this min-max is the loss that we use for the GANs. This is for discriminator and G is for the generator. So diffusion-based generative models assume that x1, xt are latent variable, and you can represent your data like this. So there is a forward diffusion chain that gradually adds noise. A variational lower bound is used to see that. So this is our denoiser. This is our reverse diffusion chain. Here at each iteration, we have this denoiser with parameter theta that we need to learn. So we define a mixture distribution that models the noisy samples obtained at any step of diffusion process with a mixture weight pi. The mixture components are Gaussian distributions with mean proportional to x and variance depending on the noise level. We use the same diffusion process and mixture distribution for both the real samples and the generated samples. So here y is the noisy samples. So here is Q of y, condition on x is a normal distribution. So by sampling y from this mixture distribution, we can obtain noisy versions of both real and generated samples with varying degree of noise. The diffusion GAN trains its generator and discriminator like this. But now your y is sampled from Q. Q is the conditional distribution of the perturbed sample given the original data. So this objective encourages the discriminator to assign high probabilities to perturbed real data and low probabilities to perturbed generated data. The generator, on the other hand, tries to produce samples that can deceive the discriminator at any diffusion step T. So the objective function 3 here, this one is very similar to the one used in the original GAN, except that it involves the diffusion steps and the perturbation functions. The diffusion steps and the perturbation function. Because now T is withdrawn from pi, p pi. So we can show that this objective also minimizes an approximation of Jensen-Shannon divergence between the true and generated distributions. But with respect to the perturbed sample and the diffusion steps. So our strategy is to make the discriminator learn from the easiest samples first, which are the original data samples, and then gradually increases the difficulty by feeding it samples from larger T. So we use a self-paced schedule. This is schedule T, which depends on the metric, this metric RD, that estimates how much the discriminator overfits to the data. RD is the same as the one used in this reference, and we calculate RD and update T every 4 millibatches. So we have two options for the distribution P that we use to sample T for the diffusion process. It can be uniform, or it can have some priority. The priority gives more weight to larger T, which means the discriminator will see more new samples from the new steps when T increases. So this is the how we update the discriminator, update the generator, and we update the diffusion. So this is some generated images of from diffusion style GAN2.